here. So we had started talking about the sizes. One second. As we had started talking about the sizes of the atoms, and I told you that across the period, the atomic radius. This is what we were discussing. That when you move across the period, the size of the atom it decreases. Why? Because you have more protons when you move to the right of the periodic table. Like you keep moving to the right, you have more protons in the nucleus. So there is more attraction for electrons. So the size of the atom is kind of smaller. So this graph over here was showing the size of the atomic radiuses. And there was one thing that we had started talking about, and that was how our atomic radius is measured. Now, I also explained that an atom has a very well-defined nucleus. So it's very easy to actually find the nucleus or exactly pinpoint where the positive charge is, where are the protons. The nucleus is very well defined. What is not very well defined is the boundary of the atom. The electrons, remember, are occupying orbitals. The electrons are all moving haphazardly. They're buzzing around like a bee around the nucleus. Maybe they're in an s orbital or a p orbital or a d orbital. So the outer boundary of the atom is kind of not properly defined. So you're not exactly sure where the boundary of the atom is. The boundary of the atom is where the electron, that would be the outer regions of the space where the electron is buzzing around. But you can't really pinpoint exactly. It's a blurred area. You can't really pinpoint exactly where that boundary ends. So it has an ill-defined boundary. So what they do is that the atomic radiuses are always measured. For example, if you have a metallic bond, so if an element is forming metallic bonds, like sodium. So if something is forming metallic bonds like sodium, it's going to have these metallic bonds the metals would lose electrons, they would form positive ions, right? So they would all start forming positive ions. And there are going to be lots and lots of these positive ions in a sea of free moving electrons. So positive ions in a sea of free moving electrons. So there would be electrons all around, delocalized electrons. That's what a metallic structure is. So coming back to our point, how do you find the atomic radius? The atomic radius is found out that the nucleus of the atom is very specific. You can easily clearly pinpoint where the nucleus is. So what you do is you measure the distance between the two nuclei and divide the distance by 2. So it's the distance between the nuclei, and that distance is supposed to be divided by 2. Is this clear? How you find the atomic radius? Yes or no? Is this clear?
Yes.
So then the other thing is that that's how you find the radius. In covalent bonding, you do pretty much the same thing. So if an element is forming covalent bonds like hydrogen, so if you've got an H2 molecule, so there's one hydrogen bonded to another hydrogen, and there are electrons being shared between them. So you measure, so there are 2 electrons being shared between them. What you do is, again, you measure the distance. It's very hard to actually predict where the electrons are, but it's very easy to actually predict, or you can clearly tell where exactly the electrons are lying. So you'll measure the distance between the 2 nuclei and divide that distance by 2. So elements that form covalent bonds, you measure the distance between the nuclei in that covalent bond. If they're forming metallic bonds, you measure the distance between the 2 nuclei in the metallic bond. But there are certain elements that don't form bonds. Those are noble gases mostly. So there's an issue with noble gases. How do you find the distance or the atomic radius of a noble gas atom? Uh, their problem is they don't form bonds. So the bigger problem is that if you have a neon atom, let's say it's got a this is a new neon atom with electrons and there's a positive nucleus, and there's another neon atom. The atoms would be very far away from each other because they're not bonding. So if you do the same technique over here, distance between the two nuclei divided by 2, you will get a large atomic radius. So, which is kind of incorrect. It's an incorrect method. So it's very hard to actually measure the atomic radius of a noble gas because the boundary of the atom is kind of ill-defined, not very well defined. So you can't really measure the boundary where it ends. But if you do the nucleus thing, that you measure the distance between the nucleus, divide that by 2, you're obviously going to get a very large distance. So for noble gases, the atomic radius is always calculated incorrectly. Like over here, if you look at the data booklet, then you would notice that the atomic radiuses are decreasing, and then all of a sudden, when you reach neon over here, that has a very large radius. I mean, it has a bigger radius compared to all of them. So the reason is that it's calculated incorrectly. Is this point clear?
Yes.
Okay, so remember that. And the other thing is, what about ions? What is the atomic radius of the ions? Now, for metals, the ion is always going to have a smaller atomic radius. Why? Because when an ion is formed, the outer shell electrons are lost. So this is the ionic. I mean, this one over here is the ionic radius. And for non-metals, because they gain electrons to form ions, their radius is always bigger than the atom. So the oxygen ion and the fluorine ion, they would be bigger in size. So anion radius is bigger because they gain electrons, and cation radius is always smaller than the atom because they lose their outer shell electrons. They always lose their outer shell electrons. And this is the graph of the atomic. So that's the graph of the atomic radius. Okay, is this clear?
Yes.
So now the other thing is that that's about it. That's all about the size of the atom. We're going to move on. Okay, the next thing. Let's. Where's the worksheet? That's this one. Now the next subtopic that we're going to do or cover is ionization energies. That's what we're going to cover. Ionization energy is you trying to remove electrons. It's the energy that is required when you try to remove electrons from an atom. So we're going to study ionization energy. It's an important topic because it gives a lot of properties. It tells you a lot about the atoms. Because all chemical reactions is all about a loss or gain of electrons. Like all bonding is similar to that. Like one atom losing electrons, the other one is gaining electrons. So ionization energy is basically when you try to remove 1 mole of electrons from an atom. So we're going to start with the first. Like if I have a sodium atom, which is gaseous, and I try to remove 1 electron from it, that is what ionization energy is. It's going to lose one electron. So, for example, over here, if I can find an image. So it's this thing. Let me just I can't copy this. So I said this is our sodium atom trying to lose one electron. So one electron is lost. So this one electron is lost. It turns into an ion. And it's a gaseous sodium atom. What gaseous means is that it's an isolated sodium atom, not bonded to anything, not attracted to anything. It's an isolated sodium atom. Whenever you have an atom that's completely isolated, that is going to be gaseous. It's it could be considered gaseous. So it's an isolated atom. You took an atom and you try to remove one electron from it. So the energy, it's always going to be endothermic. It's always, when you try to remove electrons, you have to pull it away. It's always going to be endothermic. Because the electron over here is attracted to the nucleus of the atom. So it's pretty hard to actually remove that electron. So the definition, this is known as the first ionization energy of sodium. Of sodium. And the definition for that is that it's the energy that is needed to remove. Always endothermic. You'll be asked about the definition. You'll be asked about writing the equation for ionization energy. So this is known as the first ionization energy, that remember, you have to write the states and you have to write it exactly this way if you're asked in the past paper question. So it's the energy that is needed to remove 1 mole of electrons from 1 mole of gaseous atoms to form 1 mole of gaseous plus 1 ions. Okay, that's what first ionization energy of sodium is. Energy needed to remove 1 mole of electrons from 1 mole of gaseous atoms to form 1 mole of gaseous plus 1 ions. And it should be measured under standard conditions, which is room conditions. Okay, is this clear? Yes or no? Is this clear?
Yes, sir.
Yes, sir.
So now we're also going to write the second ionization energy, that if you try to remove another electron, so let's try and remove another electron from the sodium atom, which you can. You're in the laboratory and you're free to do anything. So if you try to remove another electron, so this electron over here is going to go. Okay, so it loses another electron. This electron over here is gone. It's now going to have a charge of +2. Why? Because now it has lost 2 electrons. And so on, it could lose 3 electrons. You can have a total of, you can try and remove a total of 11 electrons. So another electron is, lost. Okay, so sodium would turn into a +2 ion because another electron is lost. So sodium turns into +1, then it turns into +2, and it would eventually turn into +3. You're in the laboratory, you can keep on removing electrons one by one. You can remove the third electron, the fourth electron. So let's talk about the second ionization energy of sodium. Okay, I'm just going to write I dot E for ionization energy of sodium. Now in the second one, remember the sodium has already lost one electron, so sodium is already +1. But now it's losing another electron and it will turn into +2. So it has lost another electron. So it has turned into +2 gaseous atom. And so what's going to happen in this is that the definition would be it's again energy needed to remove. I mean, it's exactly the same definition. It's energy needed to remove 1 mole of electrons from 1 mole of gaseous +1 ions. And to form 1 mole of gaseous +2 ions. And measured under standard conditions. So the only difference is, so measured under standard. So the only difference is that now your starting point is +1, that you've already lost, it has already lost 1 electron, now you're trying to remove the second electron. So it's going to form +2 now. Okay, is this clear?
Yes.
Okay, Mariam, is this clear? Anna? Alicia, is this clear?
Yes, sir.
Yes. Yes, sir.
Okay, so for any atom, you can have multiple ionization energies. A total of 11 ionization energies would exist for sodium. Like if I ask you what's the equation for the 7th ionization energy of sodium. So what that means is that 6 electrons have already been removed. Okay, that means sodium has already lost 6 electrons. Now you're trying to remove the 7th one. So it's going to be sodium with 6 electrons already removed. You're trying to remove the 7th one. So now it's going to become sodium 7 plus with 1 electron lost. Okay, so make sure what is meant by ionization energies. You can have the 7th or the 8th or the 10th. For example, if I talk about the 3rd ionization energy of chlorine. Now, chlorine has a total of 17 electrons. So you're sitting in the lab, you're trying to remove electrons one by one. So the third means that 2 electrons are already gone from the atom. You're trying to remove the 3rd one. So it's going to become chlorine with a charge of 3 plus. Okay, is this clear?
Yes.
So one by one, you're going to, and remember, it's going to be in sequence. Like every time, let's do a few more. If I have aluminium and the 4th ionization energy of aluminium, what's happening in this? 3 electrons are already gone. You're now trying to get rid of the 4th electron. So the 4th electron is removed and it becomes 4 plus. Okay, so make sure and remember to write down the states. This over here is going to be, it's going to be gaseous. So both of them would be in gaseous state. Is this, hopefully this is clear. Okay, what is ionization energy and what is the number, like, is it the 1st, 2nd or the 3rd or the 4th? What does that mean? Okay.
Yes.
So now the factors, like I'm trying to remove electrons. And remember, sodium doesn't, if you're confused that sodium, why is sodium losing so many electrons? Sodium usually just loses 1 electron. We're just sitting in the lab trying to forcefully remove these electrons one by one. So So this is, I mean, sodium naturally would just lose one electron. We're forcibly making it lose electrons in the lab. So we've got these isolated gaseous atoms, and we're trying to pick these electrons away from it and trying to get rid of them. So what factors would our energy? Remember, it's always energy needed to remove an electron because the nucleus is positively charged, so the electron is sticking to the nucleus. So it's kind of going to be hard for you to remove electrons because energy would be needed for that. Because the electrons are attracted, which is why it's going to be an endothermic process. Now, what factors would this depend on? For example, if I look at sodium over here and let me, here's my sodium atom. So what factors would affect the ionization energy? Would it be really hard to remove electrons? Would it be easy to remove electrons? Like what would determine which electrons are lost easily, which ones are not lost easily? So factors affecting ionization energy. Like the energy needed can be very large or it can be very less as well. So if it's very hard to remove electrons, the energy would be a lot. You would need a lot of energy to remove electrons. So can anyone tell me exactly, tell me one factor, like this electron is sticking to the nucleus, right? So what factors would make it very difficult to remove electrons? Does anyone have any idea?
If
Could be,
protons were more than electrons?
I mean, the first thing is the nucleus has protons, right? I mean, this nucleus over here is positively charged. It's because it's got protons, right? So the nucleus has protons. So if you have more protons, the electrons would be more strongly attracted to it, right? I mean, these electrons would be more strongly attracted to it. So that's one factor. Is this factor clear?
Yes.
So factor number one is that if you have more protons, which means if you have more positive nucleus or more nuclear charge, the result is there's going to be more attraction for so there's going to be more attraction for electrons, and it's going to be harder, more difficult to remove electrons. It's going to become extremely difficult. If the nucleus is very positive, then the electrons would be very strongly attracted to the nucleus. So it's going to become more difficult. So that would result in a higher ionization energy. So you got more protons. Okay, so you got more protons. That would result in a higher ionization energy. So is this factor clear? The first one. Everyone, is this clear?
Yes, sir.
Achha, let's move to the second factor. So every atom has different number of protons. Like sodium has 11 protons. You could have an atom which has, like chlorine has 17 protons. So chlorine is going to attract its electrons with more strength because it has more protons in its nucleus. So that's the first thing. That's the first major factor because it's because of the protons the electrons are attracted to the nucleus in the first place. The second factor is how far is the electron? Like you've got this electron, you've got two electrons, right? You've got an electron over here, and you've got an electron that's closer to the nucleus, like these two electrons. So if it's really far away, would it be more strongly attracted or less strongly attracted to the nucleus? Would it be easier to remove or more difficult to remove?
Easier to remove because it's more farther from the nucleus.
So it's very far away from the nucleus, which is why the force of attraction of the nucleus is going to be lesser. So the second factor is called distance. or you can call it the atomic radius as well. I mean, let's just call it distance. Distance of electron from the nucleus. So this factor is that if you are far away, you've got more distance. The electron is far away. Then it's going to be easier to remove electrons. So it's going to be easier to remove electrons, which is why that would result in a lower ionization energy. Not a lot of energy, like if the electron is very far away, not a lot of energy would be needed to kind of remove that electron. That would be kind of easy to remove. But if the electron is really close to the nucleus, then the nucleus would be holding on to that electron very strongly, and it's going to become quite difficult to remove that electron. TK, is this clear?
Yes.
Yes.
So the third factor is that's known as the shielding effect. This is the distance of electron. That's the second factor. The first one is protons. The third one is called the shielding effect, or the number of inner shells. Now this factor. What this factor is that I had a sodium atom. Let me have a lithium atom next to it. One second. This one. So let me draw two atoms. One is sodium, the other one is lithium. So let's, I mean, this is fine. And let's have, so let's have this one. So I've got two atoms next to each other. One has more shells, the other one has lesser shells. Now the thing is, remember, it's the protons that are attracted to the electrons. Like if you're trying to remove this electron, and over here you're trying to remove this electron, it's the positive nucleus in the center. This is positively charged, so the lithium over here is positively charged. That's the one that's attracting it. But there are lots of things that are coming between the electron over here and the nucleus. I mean, there are two shells coming in. There are two extra electrons that are kind of blocking the attraction. I mean, over here you can see these two electrons. Over here there's only one electron. That's known as the shielding effect. Like if you have a nucleus, let me show it over here, and there are a bunch of electrons coming in between, and there's this outer electron over here. Now the attraction for the outer electron would be lesser because you got these inner shell electrons that are coming in the way. So they are kind of blocking the attraction. The outer electron would be less attracted to the nucleus because of these inner electrons. Is this point clear?
Yes.
I don't understand.
One second. I mean, what I mean is, like in the real world, for example, if you have a magnet, right? There's North Pole and there's South Pole and there's magnetic force and there are nails over here. Okay, so let's say there are a bunch of nails. So there's a force of attraction, right? That is attracting the nails. If you start putting things in between, okay, you start putting objects, what would happen to the force of attraction for the nails? Kya hoga? Would it be
Would
weaker?
decrease.
It would decrease. Like that's so because these things that are coming in the way, they're kind of shielding the nucleus and the nails. They're blocking the force of attraction. So the same thing is kind of happening in this case as well. Like you've got you had these you had this outer electron, which is in this case it's so you had this outer electron and you had this nucleus, right? And there were these inner shell electrons, like you had lots of inner shells. So what would those inner shells do? They would decrease the force of attraction for this outer electron. Is this point clear?
Yes.
TK, is this clear to everyone? Mariam, is this clear? Alicia, Aisha, Mahad, is this
Yes.
clear? Okay. Now, so the outer electron is going to be less attracted to the nucleus if you have more inner shells. That's known as shielding effect. I mean, over here the shielding would be lesser because the outer electron is it's. I mean, there are not a lot of things that are coming in between the nucleus and the outer electron. So the force of attraction would be relatively stronger. So if you have more inner shells, there's going to be more shielding. And there's going to be a weaker force of attraction for the outer electrons. It's going to be a weaker force of attraction for the outer electrons. And since it's going to be a weaker force of attraction, it would be easier to lose that electron. Ionization energy would be lesser. So it's going to be easier to remove electrons. Okay, is this point clear?
Yes, sir.
And
Yes.
and just for clarity, I'll show you an iodine atom. Like iodine has a lot of shells. So if you look at an iodine atom, which is over here, let's just copy this. So if you look at an iodine atom, the nucleus of the iodine, it would be very hard for the nucleus of the iodine atom to kind of. So here's your positive nucleus over here in the middle, and here's your outer electron. So imagine so many. I mean, there's so many electrons that are coming in the way. I mean, the nucleus would try to pull this electron. I mean, it would be trying to pull that electron, but that's a lot of shielding. The many inner shells. So there are many initial electrons, that's high shielding. So in the case of iodine, because the nucleus is completely shielded, it's completely surrounded by electrons, so its force of attraction for its outer electrons would be very, very weak. Okay, is this point clear?
Yes.
So that one is point number 3. So that's the third factor. Remember, we've studied 3 factors. One is you have more protons in the nucleus, so electrons would be attracted strongly. It would be difficult to remove electrons. Second point was the distance. If the electron is very far away, then it would be kind of easier to remove electrons. The third point was the shielding effect or the number of inner shells. So if you've got a lot of inner shells, then again it's going to be a lot easier to remove electrons. Now moving to the fourth point. The fourth factor is So now the fourth factor is it's the net positive charge on the atom or the ion. Now this factor is that if an ion is already it already has a positive charge, like sodium. Okay, let's pick sodium. I have a neutral sodium atom, and I have a sodium atom which already has lost 8 electrons. So I have a sodium atom that has already lost 8 electrons. So this is the net positive charge, like the overall charge, because it has lost so many electrons. That's the overall positive charge. I mean, this one is neutral. It hasn't lost any electrons. This one has already lost a lot of electrons. So the net charge on this atom is, because it has lost electrons, it's plus 8. So if I try to remove electrons, this would become sodium plus 1. And this would become, the 9th electron would be lost. So that's the 9th ionization energy. But removing electrons from this would be more difficult. Because imagine if something has a charge of plus 8, it has a net positive charge of plus 8, then it's going to be attracting electrons. It would be much harder for you to remove electrons. Something that's neutral would not be, or which is neutral overall, would not really be attracting electrons that strongly. But something that is already plus 8, I mean, it already has, overall, it has a lot of positive charge. So it would have a very strong attraction for electrons. So the more the positive charge on the ion, the more difficult it's going to be for you to remove electrons. So for example, if you have iron and you've got Fe2 plus and you've got Fe3 plus, then in Fe3 plus, it would be a lot harder to remove electrons, because instead of removing it, it would be attracting electrons very strongly. So for this, it's going to be very difficult for you to remove electrons. Is this clear?
Yes.
Yep.
Okay, that's our fourth point. The more the positive charge on the thing, the more difficult it is going to be to remove electrons. And there's a fifth point which we are not going to discuss at the moment. That's the subshell and orbital arrangement. Remember, doesn't really matter in most cases. This factor is like, which subshell are you trying to remove electrons from? Is it the p subshell? Is it the s subshell? I mean, this is about that. Mostly doesn't matter. This factor is only relevant for a few specific cases. Otherwise, it's this factor over here is mostly irrelevant. Doesn't really matter. So we'll discuss the fifth factor much later on when we are almost done with the topic. So Abdullah, if you take out all electrons, you're just left with the nucleus. Like I mean, it is a possibility you can remove all the like hydrogen is just the nucleus. That's it. There are no electrons around it. Okay, so that is possible. But usually the nucleus is so positively charged that electrons are everywhere in the universe. Like they're everywhere. Wherever you go, there are electrons. So the electrons are going to come sticking around it. As I said, just remember these four factors that affect how that basically determine how strongly the electrons are attracted to the nucleus, or how easy it is to remove electrons. So we're going to discuss these four factors, and we're going to link them to the ionization energies in the next class. Okay. So let's continue tomorrow then. Okay, everyone.
Allah Hafiz.
Take care. Allah Hafiz.
Thank you.